Alright guys, so now what we're going to be doing is we're going to be using those inverse properties and one-to-one properties to help us solve word problems. So the first thing we got to remember is this is from like a couple of videos ago. Remember we had this formula A equals P times E to the RT. I call it A equals PERT, and we used it for continuous compounding. We said how much money do you have after, I don't know, 3 years has gone by at a continuous compounding rate of 7%. And we did a couple of word problems like that. We're bringing that formula back, okay? Because this formula is not just good for continuous compounding, but it can also be used to model population growth, the spread of disease, half-life, a lot of different really cool things that, that tend to move exponentially. And let me just give you a reminder of what these variables look like. A represents the accumulated amount after t years has passed. T years. So I have like a new setup going right now with my computer. So maybe my handwriting will be a little lackluster right now. Okay, so P is the principal amount, or the original amount, or your starting amount for your population. E is just a constant. R is the rate of growth. And T, like what we said before, is the amount of years or the amount of time that has passed. All right, so hopefully you remember this formula looks familiar to you. I hope it does, because guess what? This guy's going to be on your final. So we're going to bring him back a couple of times, all right? So let's get used to him now. All right, so here's our question. A population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days has passed? Okay, so the key phrase or sentence, not sentence, phrase in this question is this right here. It says the law of exponential growth. Law of exponential growth really just says, all right, go ahead and let's start using this formula. All right, so anytime you hear that a population is growing according to the law of exponential growth, then we're going to go ahead and use this formula that we see in the top left. So now our job is to really decipher what each of these sentences really mean. Let's start with the second sentence, the first half of it. It says after 2 days there are 100 flies. So what does that mean? For us, remember what A and P and R and T, what all of these things represent. What are they giving us? They're saying that after 2 days, there are 100 flies. That means T, oops, wrong pen. Maybe I should delete that for you guys. All right, so T equals 2, and this should not say 200, this should be 100. Okay, after 2 days, there are 100 flies in my population. So after 2 days has passed, there's been an accumulated amount of 100 flies in my population. So I know what T equals for the sentence, and I know what P equals for the sentence as well. Why am I saying P? I meant A. I'm sorry. I'm all over the place right now. So A is the accumulated amount. After T years has passed, which is 2, there are 100 fruit flies. So A will substitute 100 for, and T will substitute 2 for. All right, let's look at the second half of the second sentence. And after 4 days, there are 300 flies. Guess what happens this time? After 4 days has passed, there's an accumulated amount of 300 flies. So we're just going to do the same thing. So we have 2 different equations right here. The first one, we have 100 equals this whole thing, and then the second one is the 300 equals this whole thing. But what do they actually want us to solve for? They want us to solve for this, the accumulated value, A, equaling P times E to the R after 5 years has after 5 days has passed. So they want us to solve for this. And it's not that hard to solve for this guy. As long as we know what R is and what P is. If we know the original population size and the rate of growth, it will be easy to calculate how many flies there will be after 5 days. But the thing is this, we only have these two equations to work with. We only have this guy and this guy to work with, but that's okay because they both contain P and R. Anytime you have two unknowns and two equations, we're able to solve for both of them actually. So this is how we're going to go about doing that. What I'm going to do is I'm going to take that first equation and I'm going to solve for one of the variables. I can solve for P or I can solve for R. P is a little bit easier, so I went ahead and did that. Let's zoom in over here. So you see, I took that first equation of 100 equals P times e to the R2, and I solved for P by dividing both sides by e to the R2. This says that the original population of flies is equal to this whole sentence right here, this whole phrase. That's how many flies were in my original population. But I can't tell you an exact number. Why? Because I don't know what R is. That didn't work out. If I knew what R was, then I would be able to tell you what the original population was. I'm just going to make a smaller pen. All right. So once I solve for either of the variables, I'm going to take this P and I'm going to plug it into the second equation. All right. So wherever I'm going to take the second equation, 300 equals P times e to the R4, and I'm going to plug in this P in for this guy. So it's going to look like this. I have 300, this is my second equation now, equals P times e to the R4, and I'm replacing P with this P that I solved for over here. Hopefully everyone can see what I just did. So what am I left with? I'm left with 300 equals 100 divided by e to the R2 times e to the R4. So in the next step, what I did is I divided both sides by 100. I divided both sides by 100. So 300 divided by 100 is 3. And when I divide my right-hand side by 100, this 100 cancels out with this 100. So I'm just left with e to the R4 divided by e to the R2. It might make more sense if I wrote it like this, because we're used to seeing the numbers in front of the variables. That should be an e. To R. Jesus. Okay, so I have, maybe that form is a little bit more user-friendly. We're able to see what's actually happening. So remember, if I have an exponent in the denominator, in our case is e to the 2r, I can put him back into the numerator as long as I make that exponent have a negative, right? So if I want to put this guy back in the numerator, I'm going to put a negative in his exponent. So rather than having 2r, I'm going to have negative 2r. And that's what I did in the next step. The reason why I did that is because now I can combine my exponents. Remember, anytime I have two similar bases being multiplied to each other, I can just add their exponents, right? So if I have x to the 4th times x squared, this is equal to x to the 4 plus 2, which is x to the 6th. So that's what I did. Because they both have the same base, instead of x, they have the same base e, and they're being multiplied by to each other, I can just add their exponents, will leave me with 3 equaling e to the 2r. Okay, so this is great because now we have one equation with one unknown. And guess what? We can now solve for r. So, I don't know what's going on with my computer. Okay, freak accident. Let's keep moving on. All right, so now our goal is to solve for 3 equals 2 to the r. I have my variable stuck in the exponent, so I have to undo this base. The way I undo this base is by applying ln to both sides, right? If I use log base e of e to the 2r, this should just equal 2r according to the inverse property. I'm undoing these guys using the inverse property. So in this next step, ln and e end up canceling out, so I'm left with just 2r. Now I know that r is equal to ln of 3 divided by 2. A lot of work just to solve for one variable, I know. But the reason why I did a long-winded question like this is they might ask you to do something like this on Pearson. So just trying to help you out. Okay, so now that we found out what r was, let's find out what p is. So let's use either of the formulas. I'm going to use the first one, 100 equals p times e r2. But now I know what r is, right? I know what r is, so I'm going to plug in our newfound r. Alrighty, so if I simplify, these twos cancel out because I have 2 divided by 2, which is just 1. So I have 100 equals p times e to the ln of e. But if you guys remember, if I have e raised to the log base e of 3, these guys, because they have the same base, will cancel each other out, and it'll just leave me with a 3. This means my sentence actually says 100 equals 3 times p. So that means p, my initial population, is 100 divided by 3, which is 33.3 repeating, right? So guess what? I've solved for my initial population, which is p, or my original population, which is p, and I solved for the rate of growth, which was r, which is ln of 3 divided by 2. And now I can just take those pieces of information and answer the actual question we were asking. How many flies are there after 5 years? So this 5 represents t, this ln of 3 over 2 represents r, and this 100 over 3 represents the p. I have everything in place for me to solve for how many flies there will be after 5 days. So the answer here is 519.62. I don't know how you have 0.62 of a fly, but you do. No, honestly, you would just round it. Alrighty. So the big question is, should we do this next question now or save it for the next video? Let's just do it now. Kill it. Alright, so here's a cool question. It's actually 2 questions, but they're pretty quick. After 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Find the exponential decay model for carbon-14. So they want us to find the exponential decay model. So this A equals PERT. Well, that is the exponential model, but without the variables filled in. So we know we have to use this formula, A equals PERT. So what we're going to do now is we're going to fill in the things that are given to us, okay? So I'm going to go ahead and fill in t, because we know how many years have passed. 5,715. So that's t right here. And now, why do I have a p over 2 on the left-hand side? Remember what the left-hand side represents. This a. What does the a represents? how much of your original population or substance is left after T years has passed? Well, they said after 5,715 years have passed, half of the original amount is left. So if P is the original amount, half of the original amount is P divided by 2. So I have P divided by 2 amount is left after 5,715 years have passed. I hope that makes sense. Okay? Alrighty. So what I did in this next step, well, let me tell you. Right now, our goal is to solve for r, right? And the first thing I'm going to do is I'm going to divide both sides by p. If I divide both sides by p, all the p's cancel out. So we don't even have to worry about that, that variable. This is great because we went from having 2 unknowns in our equation to just 1. And whenever we have one equation with 1 unknown, we can most likely solve for that variable. So I have 1/2 equals e to the r times 5,715. How do I undo this e right here? Well, I take ln of it, right? I use the inverse property. If I take ln of both sides, everything on the right-hand side cancels except for r times 5,715. So what does that mean? What does r equal? If I divide both sides by 5,715, I'll get my answer. So r is approximately, I rounded this answer, minus 0.000121. So we figured out what r was. So this is what the, remember what the question is asking us. Find the exponential decay model for carbon-14. So given a certain amount of carbon-14, this is the rate at which it's decaying. And if we know what T is, if we fill in T, we'll know how much is left. We got to get good at reading these sentences. And it's going to make a little bit more sense once we do the second half of this question. Okay. When the Dead Sea Scrolls were discovered, it was shown that 76% of their original carbon-14 remained. Find how old the Dead Sea Scrolls are. So I think you guys have heard of this before, carbon dating rate. I think so. This is just an example of how exponentials come in use. Although I heard carbon dating doesn't just use carbon-14, it also uses carbon-12. But what do I know? I'm not a chemist or anything like that. So I don't know. I'll just follow this textbook example. All right. So what's decaying here is carbon-14. So what I'm going to use is what we solved in the previous one, the exponential decay model for carbon-14. See, that's why we had to do it back to back, because they're related. So we just figured out what the model for carbon-14 looks like, and now we're going to go ahead and use that model to kind of gauge how old the Dead Sea Scrolls are. So what they say is that 76% of their original carbon-14 remains. That means if P was the original amount of carbon-14 in the Dead Sea Scrolls, 76% of the carbon-14 of the original would just be P times 0.76. So if P was the original, then 76% of the original is 0.76 times P. Alrighty, so remember what we're trying to solve here. We're trying to find the age of the Dead Sea Scrolls. And that means we're solving for some sort of time. And that's great. That works out for us because T is really the only variable that we need to solve for. Yes, there is P right here as well. We don't know what P equals, but guess what? We can always divide those P's out and we're only left with T. If we can solve for T, we can figure out the age of the Dead Sea Scrolls. Pretty cool, right? Okay, so how do we go about doing that? Well, right now T is stuck in the exponent of this base E. How do we undo that base E? Well, we apply the log, or the log base E of it. or the ln function. So if I take ln of both sides, what happens to this e and this ln? They cancel each other out, and I'm just left with ln of 0.76 equals negative 0.000121 times t. So guess what t is? We just divide both sides by minus 0.0000121, and you're probably going to have to use a calculator for this. But if you plug it into your calculator, you'll find out that t is equal to 2,268. So that means the Dead Sea Scrolls are approximately 2,268 years old from the time that they were discovered. So it's pretty cool. Pretty useful stuff, right? I think that's kind of interesting if you ask me. All right, guys, so I think we're done with our log chapter and our exponential chapter. Let's see what we have next.